Okay, so this is going to be a video about the dreaded Taylor and Maclaurin series. Okay, so if you recall, we said that there's this animal called a power series, which goes from n equals 0 to infinity, that has a series of coefficients next to a series of variables centered at some value a. And one of the things that we want to note is that sometimes over certain intervals, these things can be used in place of a function. So we've actually seen that if I take the function 1 over 1 minus x, this is the same as the series n equals 0 to infinity for x sub n, so long as the absolute value of x is less than 1. So on this interval, this function can be replaced by that series. Now, that's kind of straightforward because that stems from the fact that this is a geometric series, and that when this is the case, I get this as the sum. However, not everything is a geometric series, and not all power series are geometric, because this first term can be dependent on n, and in a geometric series, the first term is a constant. All right, so how do we find a way to be able to make these type of connections? If you give me a function, how do I get a series, and where does these two things equal each other? Okay, so the tool that we actually use to do this, of all things, is the derivative. All right, so that's kind of unexpected, but we're coming back into use of the derivative. So let's see how that plays out. Okay, so what we want is f of x to equal some power series, n equals 0 to infinity, c sub n at x minus a to the n, when I'm on some interval, right? So the distance between x and a is less than some value r. This is what I'm looking for. Okay, so this statement would say that if this is going to work, f of x is like c0 plus c1x minus a plus c2x minus a squared plus c3x minus a cubed plus c4x minus a to the fourth, and so forth and so on. All right, so I'm giving myself a bunch of terms to work with here, and we'll see why I did that in a minute. I want you to first note that if I take f of a, so I put an a in for all of these x's, all of these go to 0, and that leaves me with c sub 0. Okay, that's an important note. That's going to come up later on in our little process here. So the first thing is to take the first derivative of this series. So if I take the first derivative, I get f prime of x, right, is going to be c sub 1 plus 2c sub 2 x minus a plus 3c sub 3 x minus a squared plus 4c sub 4 times x minus a cubed, and so forth and so on. All right, so I want to note also that f prime of a happens to equal c1. Okay, so let's do it again. F double prime of x gives me 2c2 plus 3 times 2c sub 3 x minus a plus 4 times 3 c sub 4 x minus a squared plus so forth and so on. And this time I'm going to note that f double prime of a is just 2c2. Okay, so let's do it one more time. Why not? All right, so the third derivative of x comes out as 3 times 2c sub 3 plus 4 times 3 times 2 c sub 4 x minus a squared plus yada yada. Okay, so again, I'm going to note that I get f triple prime of a is going to be 3 factorial times c sub 3. Okay, so this is literally 0 factorial times c0, 1 factorial times c1, 2 factorial times c2, and 3 factorial times c3. Okay, so if I kept going on this, I'm going to get some interesting results. Okay, so note, I have that f of a is c0, f prime of a is c1, f double prime of a is 2c2, f triple prime of a is going to be 3 factorial c sub 3, and I said that's 0 factorial c0, 1 factorial c1, 2 factorial c2, and 3 factorial c3, and that, if you keep going, keeps going on and on, where we can say that the nth derivative of a is n factorial times c sub n. Now this is the important fact, because I can rewrite that to say that c sub n is the nth derivative of a over n factorial. This means that I should be able to rewrite f of x as the series from n equals 0 to infinity, right, of the nth derivative of a over n factorial times x minus a to the nth. And this is what we're going to call the Taylor series formula. So this will occur when the series converges. So for values of x for which this series converges, this function is equal to this series. So what I have done is I've essentially turned any analytic function that's differentiable into a sum of terms, and I know the coefficients for it. Basically, I've turned it into something that looks like a polynomial, which is actually useful for doing calculations, and we'll get into some of that a little bit later on, but that's what's going on here. So this is basically a Taylor series. Okay, so let's get to kind of a clean board. Okay, so a Taylor series is f of x is equal to the sum from n equals 0 to infinity of the nth derivative of f at a over n factorial times x minus a to the n. A Maclaurin series is just a special case of a Taylor series where a equals 0. So this would be f of x being the sum from n equals 0 to infinity of the nth derivative of f at 0 divided by n factorial just times x to the n. Okay, so let's give an example of this, okay? Because at some point we also have to discover, like, where does this thing converge, and that's easier to do with a specific example. So let's find the Maclaurin series for f of x equals e to the x. Now, you'll see why I picked e to the x in a few minutes, because it's the easiest thing to take the derivative of. Okay, so we're going to try to build the derivatives, right? So f of x is e to the x. It's Maclaurin, so I'm centering at 0. So f of 0 is just 1. f prime of x, well, lo and behold, that's also e to the x. So f prime of 0 is 1. F double prime of x, again, is e to the x. F double prime of 0 is also 1. Okay, so this is a unique situation where every derivative of f with respect to x is e to the x, and every derivative of x, or every derivative of f with respect to x at 0 is 1. Okay, so this means that if I use my Taylor formula, f of x is the sum from n equals 0 to infinity of f n of 0 over n factorial times x to the n. This becomes the sum from n equals 0 to infinity of 1 over n factorial, because all of these are just 1. Now, they don't always come out that way, but the coefficient here is just 1 over n, x to the n, which means that e to the x is equal to the sum from n equals 0 to infinity, x to the n over n factorial. Now, that seems almost too good to be true, but in fact, this is the series. And the question is like, where does this converge? Where does it converge? Well, how do we do that? We use the ratio test. Okay, so we just established that the series from n equals 0 to infinity of x to the n over n factorial is e to the x. But we need the ratio of convergence. So we take we need the interval of convergence. So we take the limit as n approaches infinity of n plus 1 factorial over x to the n plus 1 times, oops, that's not right. I got that upside down. It's x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. This becomes the limit as n approaches infinity of, let's see, 1 over n plus 1 times the absolute value of x, which that limit goes to 0, which is always less than 1, which means this thing converges for all x values. Okay, so what we're saying here is that e to the x is equal to n equals 0 to infinity of x to the n over n factorial, regardless of what x value you pick. Okay, so that's kind of unique. This is for all x. Now, this gives us a set of 2. You got this one, and you also have this, right, is n equals 0 to infinity x to the n. But this one only converges, recall, when x is between -1 and 1, right? So this gives us 2 actual power series that converge to specific functions. And we'll take a look at a bunch more later. But there you go. There's an introduction to Taylor and Maclaurin series and the Maclaurin series for e to the x.